Electric current. Describe the flow of electric charge. Describe what is happening inside a current carrying wire. Give examples of voltage sources. Describe the factors that affect the resistance of wire. Describe Ohm's law. Explain the causes of electric shock. Distinguish between DC and AC. Describe how AC is converted to DC. Describe the drift speed of conduction electrons in a current carrying wire. Identify the source of conduction electrons in a circuit. Relate the electric power used by a device to current and voltage. Let's look at the big idea. Electric current is related to the voltage that produces it and the resistance that opposes it. The previous chapter discussed the concept of electric potential or voltage in terms of energy per charge. We'll see in this chapter that voltage can be thought of as an electric pressure that produces a flow of charge or current within a conductor. The flow is restrained by the resistance it encounters. When the flow takes place along one direction, it is called direct current, DC. When the charge flows to and fro, it is called alternating current, AC. The rate at which energy is transferred by electric current is power. These ideas are better understood if you know how they relate to one another. Let's begin with the flow of electric charge. How can you make a simple voltage source? Soak a piece of paper towel in a salt solution or vinegar and place it between a dime and a penny. Attach one lead from a galvanometer to each of the coins. Now, attach the lead that was originally attached to the dime to the penny and vice versa. Analyze and conclude. Observing. Describe the galvanometer reading when the leads were brought in contact with the coins. What happened when the leads were reversed? Predicting. What do you think would happen if a number of these dime and penny cells were connected in series, that is, placed end to end with dimes touching pennies? Making generalizations, how do you think voltage sources such as the batteries used in portable electronic devices are constructed? 34.1. Flow of charge. Recall that heat flows through a conductor when a difference in temperature exists between its ends. Heat flows from the end of higher temperature to the end of lower temperature. When both ends reach the same temperature, the flow of heat ceases. Charge flows in a similar way. When the ends of an electric conductor are at different electric potentials, charge flows from one end to another. Charge flows when there is a potential difference or difference in potential voltage between the ends of a conductor. The flow of charge will continue until both ends reach a common potential. When there is no potential difference, there is no longer a flow of electrons through the conductor. As an example, if one end of a wire were connected to a ground and the other end placed in contact with a sphere of a Van de Graaff generator that is charged to a high potential, a surge of charge would flow through the wire. The flow would be brief, however, for the sphere of the generator would quickly reach a common potential with the ground. To attain a sustained flow of charge in a conductor, some arrangement must be provided to keep one end at a higher potential than the other. The situation is analogous to the flow of water from a higher reservoir to a lower one, as shown in figure 34.1a. 34.1a. Water flows from higher pressure to lower pressure. The flow will cease when the difference in pressure ceases. B, water continues to flow because a difference in pressure is maintained with the pump. Water will flow in a pipe that connects the reservoir only as long as a difference in water level exists. The flow of water in the pipe, like the flow of charge in the wire that connects the Van de Graaff generator to the ground, will cease when the pressures at the two ends are equal. Notes: electrons in the wire are like water in a pipe. Whenever a little water enters one end, almost immediately the same amount of water exits the other end. In order that the flow be sustained, there must be a suitable pump of some sort to maintain a difference in water levels, as shown in figure 34.1b. Then there will be a continual difference in water pressures at a continual flow of water. The same is true of electric current. Concept check. What happens when the ends of a conductor are at different electric potentials? 34.2. Electric current. Electric current is the flow of electric charge. In solid conductors, the electrons carry the charge through a circuit because they are free to move throughout the atomic network. These electrons are called conduction electrons. Protons, on the other hand, are bound inside atomic nuclei that are more or less locked in fixed positions within the conductor. In fluids, such as the electrolyte in a car battery, positive and negative ions as well as electrons may compose the flow of electric charge. Measuring current. Electric current is measured in amperes, for which the SI unit is the symbol A. An ampere is the flow of 1 coulomb of charge per second. Recall that 1 coulomb of standard unit of charge is the electric charge of 6.24 billion billion. In a wire that carries a current of 5 amperes, for example, 5 coulombs of charge pass through any cross-section in the wire each second. That's a lot of electrons. In a wire that carries 10 amperes, twice as many electrons pass any cross-section each second. Figure 24.2 shows a simplified view of electrons flowing in a wire. Figure 34.2, when the rate of flow of charge past any cross-section is 1 coulomb, 6.24 billion electrons per second, the current is 1 ampere or 1 amp. Net charge of a wire. A current-carrying wire has a net electric charge of 0. While the current is flowing, negative electrons swarm through the atomic network that is composed of positively charged atomic nuclei. Under ordinary conditions, the number of electrons in the wire is equal to the number of positive protons in the atomic nuclei. When electrons flow in a wire, the number entering one end is the same as the number leaving the other. So we see that the net charge of the wire is normally 0 at every moment. Concept check. What is the net flow of electric charge in a current-carrying wire? 34.3. Voltage sources. Charges do not flow unless there is a potential difference. A sustained current requires a suitable electric pump to provide a sustained potential difference. Something that provides a potential difference is known as a voltage source. If you charge a metal sphere positively and another negatively, you can develop a large voltage between them. This is not a good voltage source because when the spheres are connected by a conductor, the potentials equalize in a single brief surge of moving charges. It is not practical. Batteries and generators, however, are capable of maintaining a continuous flow. Steady voltage sources. Voltage sources such as batteries and generators supply energy that allow charges to move steadily. In a battery, a chemical reaction occurring inside releases electrical energy. Generators such as the alternators in automobiles convert mechanical energy to electrical energy as will be discussed in Chapter 37. The electrical potential energy produced by whatever means is available at the terminals of a battery or generator. The potential energy per coulomb of charge available to electrons moving between terminals is the voltage, sometimes called the electromotive force or EMF. The voltage provides the electric pressure to move electrons between the terminals in a circuit. Power utilities use electrical generators to provide the 120 volts delivered to home outlets. The alternating potential difference between the two holes in the outlet averages 120 volts. When the prongs of the plug are inserted in the outlet, an average electric pressure of 120 volts is placed across the circuit connected to the prongs. This means that 120 joules of energy is supplied to each coulomb of charge that is made to flow in the circuit. 34.3. Each coulomb of charge that is made to flow in a circuit that connects to the ends of this 1.5 volt flashlight cell is energized with 1.5 joules. Distinguishing between current and voltage. There is often some confusion between charge flowing through a circuit and voltage being impressed across the circuit. To distinguish between these ideas, consider a long pipe filled with water. Water will flow through the pipe if there is a difference in pressure across the pipe or between the ends. Water flows from the high pressure end to the low pressure end. Only the water flows, not the pressure. Similarly, charges flow through a circuit because of an applied voltage across the circuit. You don't say that voltage flows through a circuit. Voltage doesn't go anywhere, for it is the charges that flow. Voltage causes current. Concept check. What are the two voltage sources used to provide the energy that allows charges to move steadily? 34.4. Electric resistance. The amount of charge that flows in a circuit depends on the voltage provided by the voltage source. The current also depends on the resistance that the conductor offers to the flow of charge. The electric resistance, this is similar to the rate of water flow in a pipe, which depends not only on the pressure difference between the ends of the pipe, but on the resistance offered by the pipe itself, as shown in figure 34.4. Notes: a material with a low resistance has high conductivity. 34.4. For a given pressure, more water passes through a large pipe than a small one. Similarly, for a given voltage, more electric current passes through a large diameter wire than a smaller one. The resistance of a wire depends on the conductivity of the material used in the wire, that is, how well it conducts, and also on the thickness and length of the wire. Thick wires have less resistance than thin wires. Longer wires have more resistance than short wires. In addition, electric resistance depends on temperature. The greater the jostling about of the atoms within the conductor, the greater resistance the conductor offers to the flow of charge. For more conductors, increased temperature means increased resistance. The resistance of some materials becomes zero at very low temperatures, a phenomenon known as superconductivity. Certain metals acquire superconductivity, zero resistance to the flow of charge, at temperatures near absolute zero. Since 1987, superconductivity at high temperatures above 100 Kelvin has been found in a variety of nonmetallic compounds. Once electric current is established in a semiconductor, the electrons flow indefinitely. Electric resistance is measured in units called ohms, after George Simon Ohm, 1789 to 1854, a German physicist who tested different wires and circuits to see what effects the resistance of wires had on current. Concept check. What factors affect the resistance of a wire? Figure 34.2. A simple hydraulic circuit is analogous to an electric circuit. 34.5 Ohm's law. The relationship among voltage, current, and resistance is called Ohm's law. Ohm's law states that the current in a circuit is directly proportional to the voltage impressed across the circuit and inversely proportionate to the resistance of the circuit. In short, current equals voltage over resistance. Figure 34.6. The stripes on these resistors are color-coded to indicate the resistance in ohms. The relationship among the units of measure for these three quantities is as follows. 1 ampere equals 1 volt per ohm. For a given circuit of constant resistance, current and voltage are proportional. This means that you'll get twice the current through a circuit for twice the voltage across the circuit. The greater the voltage, the greater the current. But if the resistance is doubled for a circuit, the current will be half what it would be otherwise. The greater the resistance, the less the current. Ohm's law makes good sense. How much current is drawn by a lamp that has a resistance of 100 ohms when the voltage is 50 volts is impressed across it? Current equals voltage over resistance, which equals 50 over 100, which equals 0.5 amps. Using specific values of potential difference of 1 volt impressed or imposed across a circuit that has a resistance of 1 ohm will produce a current of 1 amp. If a voltage of 12 volts is impressed across the same circuit, the current will be 12 amps. The resistance of a typical lamp cord is much less than 1 ohm, while a typical light bulb has a resistance of about 100 ohms. Notes: using I for current, V for voltage, and R for resistance, Ohm's law reads I equals V over R. An iron or electric toaster has a resistance of 15 to 20 ohms. The low resistance permits a large current that produces considerable heat. The current inside electric devices such as radio and television receivers is regulated by current elements called resistors, whose resistance may range from a few ohms to millions of ohms. Concept check. What does Ohm's law state? I equals V over R. Remember. 34.6 Ohm's law and electric shock. What caused the electric shock in the human body? Current or voltage? The damaging effect of electric shock are the result of current passing through the body. For Ohm's law, we can see that this current depends on the voltage applied and also on the electric resistance of the human body. The body's resistance. The resistance of your body depends on its condition and ranges from about 100 ohms if you're soaked with salt water to about 500,000 ohms if your skin is very dry. If you touch the two electrodes of a battery with your dry fingers, the resistance your body would normally offer to the flow of electrons would be about 100,000 ohms. You usually would not feel 12 volts, and 24 volts would just barely tingle. If your skin were moist, on the other hand, 24 volts would be quite uncomfortable. Table 34.1 describes the effects of different amounts of current on the human body. Many people are killed each year by current from common 120 volt electric circuits. If you touch a faulty 120 volt light fixture with your hand while you are standing on the ground, there is a 120 volt electric pressure between your hand and the ground. The soles of your shoes normally provide a very large resistance between your feet and the ground, so the current would probably not be enough to do serious harm. But if you are standing barefoot in a wet bathtub, connected through its plumbing to the ground, the resistance between you and the ground is very small. Your overall resistance is lowered so much that a 120-volt potential difference may produce a harmful current through your body. Drops of water that collect around the on-off switch of devices such as a hairdryer can conduct current to the user. Although distilled water is a good insulator, the ions in ordinary water greatly reduce the electric resistance. There is also usually a layer of salt left from perspiration on your skin, which when wet lowers the skin resistance to a few hundred ohms or less. Handling electric devices while taking a bath is extremely dangerous. 34/7, handling a wet hair dryer can be like sticking your fingers into a live socket. Think, if the resistance of your body were 100,000 ohms, what would be the current in your body when you touch the terminals of a 12-volt battery? Current equals voltage over resistance. Current equals 12 volts over 100,000 ohms equals 0.00012 amps. Harmless. If your skin were very moist so that your resistance was only 1,000 ohms and you touched the terminals of a 24-volt battery, how much current would you draw? You would draw 12 volts divided by 1,000 ohms, or 0.024 amps, a very dangerous current. High voltage wires. You probably have seen birds perched on high voltage wires like the ones in figure 34.8. Every part of the bird's body is at the same high potential as the wire, and it feels no ill effects. For the bird to receive a shock, there must be a difference in potential between one part of its body and another. Most of the current will then pass along the path of least electrical resistance connecting these 2 points. Suppose you fall from a bridge and manage to grab onto a high voltage power line, halting your fall. So long as you touch nothing else of different potential, you will receive no shock at all. Even if the wire is thousands of volts above ground potential, and even if you hang by it with 2 hands, no charge will flow from one hand to the other. Figure 34.8, the bird can stand harmlessly on one wire of high potential, but it better not grab the neighboring wire. This is because there is no appreciable difference in electric potential between your hands. If, however, you reach over with one hand and grab onto a wire of different potential, zap. Ground wires. Mild shocks occur when the surfaces of appliances are at an electric potential different from that of the surfaces of other nearby devices. If you touch surfaces of different potentials, you become a pathway for current. To prevent this problem, the outsides of electric appliances are connected to a ground wire, which is connected to the round third prong of a 3-wire electric prong, shown in figure 34.9. All ground wires in all plugs are connected together through a wiring system of the house. Figure 34.9. The third prong connects the body of the appliance directly to the ground. Any charge that builds up on the appliance is therefore conducted to the ground, a ground wire. The 2 flat prongs are for the current carrying double wire. If the live wire accidentally comes in contact with the metal surface of an appliance, the current will be directed to ground rather than shocking you if you handle it. Health effects. One effect of electric shock is to overheat tissue in the body or to disrupt normal nerve functions. It can upset the nerve center that controls breathing. In rescuing victims, the first thing to do is clear them from the electric power supply with a wooden stick or some other non-conductor so that you don't get electrocuted yourself. Then apply artificial respiration. Concept check. What causes the damaging effects of electric shock? 34.7. Direct current and alternating current. Electric current may be DC or AC. By DC, we mean direct current, which refers to the flow of charge that always flows in one direction. A battery produces direct current in a circuit because the terminals of the battery always have the same sign of charge. Electrons always move through the circuit in the same direction, from the repelling negative terminal and towards the attracting positive terminal. Even if the current moves in unsteady pushes, so long as it moves in one direction only, it is DC. Alternating current, AC, as the name implies, is electric current that repeatedly reverses direction. Electrons in the circuit move first in one direction and then in opposite direction, alternating back and forth about relatively fixed positions. This is accomplished by alternating the polarity of the voltage at the generator or other voltage sources. Nearly all commercial AC circuits in North America involve voltages and current that alternate back and forth at a frequency of 60 cycles per second. This is 60 hertz current. In some places, 25 hertz, 30 hertz, and 50 hertz current is used. By plotting current over time, as shown in figure 3410, you can illustrate the difference between DC and AC. DC flows in only one direction over time. AC cycles back and forth over time. Figure 3410. A. Direct current does not change direction over time. B. Alternating current cycles back and forth. Voltage standards. Voltage of AC in North America is normally 120 volts. In the early days of electricity, higher voltages burned out the filaments of electric light bulbs. Tradition has it that 110 volts was settled on because it made bulbs of the day glow as brightly as a gas lamp. So the hundreds of power plants built in the United States prior to 1900 adopted 110 volts or 115 or 120 volts as their standard. By the time electricity became popular in Europe, engineers had figured out how to make light bulbs that would not burn out so fast at higher voltages. Power transmission is more efficient at higher voltages, so Europe adopted 220 volts as their standard. The United States stayed at 110, today officially 120 volts, because of the installed base of the 110 volt equipment. 3-wire service. Although lamps in an American home operate on 110 to 120 volts, many electric stoves and other energy-hungry appliances operate on 220 to 240 volts. How is this possible? Because most electric service in the United States is 3-wire. One wire at 120 volts positive, one wire at 0 volts neutral, and the other wire at a negative 120 volts. This is AC, with the positive and negative alternating at 60 hertz. A wire that is positive at one instance is negative 120th of a second later. Most home appliances are connected between the neutral wire and either of the other two, producing 120 volts. When the plus 120 is connected to the minus 120, a 240 volt jolt is produced, just right for electric stoves, air conditioners, and clothes dryers. Ventricular fibrillation may be induced by only 0.06 amps through the chest for a fraction of a second from a common 120 volt circuit. Inducing the same effect with direct current requires about 0.3 to 0.5 amps. If the current has a direct pathway to the heart via a cardiac catheter or other electrode, less than 0.001 amps can cause fibrillation. The popularity of AC rises from the fact that electric energy in the form of AC can be transmitted great distances with enough voltage step-ups that result in lower heat losses in the wires. Why this is so will be discussed in Chapter 37. The primary use of electric current, whether DC or AC, is to transfer energy quietly, flexibly, and conveniently from one place to another. Concept check. What are the two types of electric current? 34.8. Converting AC to DC. The current in your home is AC. The current in battery-operated devices, such as laptop computers or cell phones, is DC. With an AC-DC converter, you can operate a battery-run device on AC instead of batteries. In addition to a transformer to lower the voltage, Chapter 37, the converter uses a diode, a tiny electric device that acts as a one-way valve to allow electron flow in only one direction. Since alternating current vibrates in two directions, only half of each cycle will pass through a diode. Figures 3411A and 3411B. 3411A. When input to a diode is AC. B. Output is pulsating DC. C. Charging and discharging of a capacitor provides continuous and smoother current. D. In practice, a pair of diodes are used so there are no gaps in current output. 3412. Diodes are tiny devices that allow electrons to flow in only one direction. The output is rough DC, off half the time. To maintain continuous current while smoothing the bumps, a capacitor is used. Figure 3411C. Notes: a familiar diode is the light-emitting diode seen on clocks and instrument panels. A solar cell is a LED in reverse. It absorbs light and produces electricity. Recall from the previous chapter that a capacitor acts as a storage reservoir for charge. Just as it takes time to raise or lower the water level in a reservoir, it takes time to add or remove electrons from the plates of a capacitor. A capacitor therefore produces a retarding effect on changes in current flow. It smooths the pulsed output. Concept check. How can you operate a battery-run device on AC? 34.9. The speed of electrons in a circuit. When you flip on a light switch on your wall and the circuit is completed, the light bulb appears to glow immediately. Energy is transported through the connecting wires at nearly the speed of light. The electrons that make up the current, however, do not move at this high speed. At room temperature, the electrons inside a metal wire have an average speed of a few million kilometers per hour due to their thermal motion. This does not produce a current because the motion is random. There is no net flow in any one direction. But when a battery or generator is connected, an electric field is established inside the wire. It is a pulsating electric field that can travel through a circuit at nearly the speed of light. The electrons continue their random motions in all directions while simultaneously being nudged along the wire by the electric field. The conducting wire acts as a guide or pipe for electric field lines, as you can see in figure 3413. In the space outside the wire, the electric field has a pattern determined by the location of electric charges, including charges in the wire. Inside the wire, the electric field is directed along the wire. If the voltage source is DC like the battery shown in figure 3413, the electric field lines are maintained in one direction in the conductor. Figure 3413, the electric field lines between the terminals of a battery are directed through a conductor, which joins the terminals. Figure 3414, the solid lines depict a random path of an electron bouncing off atoms in a conductor. The dashed lines show an exaggerated view of how this path changes when an electric field is applied. The electron drifts towards the right with an average speed less than a snail's pace. Conduction electrons are accelerated by the field. Before the electrons gain appreciable speed, they bump into the anchored metallic ions in their path and transfer some of their kinetic energy to them. This is why current-carrying wires become hot. In a current-carrying wire, collisions interrupt the motion of the electrons so that their actual drift speed or net speed through the wire due to the field is extremely low. A typical DC circuit in the electrical systems of an automobile, for example, electrons have a net average drift speed of about 0.01 centimeters per second. At this rate, it would take about 3 hours for an electron to travel through 1 meter of wire. In an AC circuit, the conduction electrons don't make any net progress in any direction. Notes, caution, don't short out the terminals of a battery as shown in figure 3413. If you touch both terminals with a metal wrench, for instance, you can create a spark that can ignite hydrogen gas in the battery and send pieces of the batteries and acid flying. Figure 3413. The electric field lines between the terminals of a battery are directed through a conductor which joins the terminals. In a single cycle, they drift in a tiny fraction of a centimeter in one direction and then the same tiny distance in the opposite direction. Hence, they oscillate rhythmically to and fro about relatively fixed positions. When you talk to your friend on a conventional telephone, it is the pattern of oscillating motion that is carried across town at nearly the speed of light. The electrons already in the wires vibrate to the rhythm of the traveling pattern. In a cell phone, as you'll see in chapter 39, the electrons dance to the rhythmic pattern of electromagnetic waves in the air. Concept check. Why is the drift speed of electrons in a current-carrying wire extremely low? Electrolysis, linked to electrochemistry. Electrochemistry is about electrical energy and chemical change. Molecules in a liquid can be broken apart and separated by the action of electric current. This is electrolysis. A common example is the passing of electric current through water, separating water molecules into hydrogen and oxygen components. This common process is also at work when a car battery is recharged. Electrolysis is also used to produce metals from ores. Aluminum is a familiar metal produced by electrolysis. Aluminum is common today, but before the advent of this production by electrolysis in 1886, aluminum was much more expensive than silver or gold. 3410. The source of electrons in a circuit. In a hardware store, you can buy a water hose that is empty of water, but you can't buy a piece of wire that is an electron pipe that is empty of electrons. The source of electrons in a circuit is the conducting circuit material itself. Some people think that the electric outlets in the wall of the homes are the source of electrons. They think that electrons flow from the power utility through the lines, the power lines, and into the wall outlets of their homes. This is not true. The outlets in homes are AC. Electrons do not travel appreciably distances through a wire in an AC circuit. Figure 3415. The conduction electrons that surge to and fro in the filament of a lamp do not come from the voltage source. They are in the filament to begin with. The voltage source simply provides them with surges of energy. Instead, they vibrate to and fro about relatively fixed positions. When you plug a lamp into an AC outlet, energy flows from the outlet into the lamp, not electrons. Energy is carried by the electric field and causes a vibratory motion of the electrons that already exist in the lamp filament. If 120 volts AC are impressed on a lamp, then an average of 120 joules of energy are dissipated for each coulomb of charge that is made to vibrate. Most of this electrical energy appears as heat, while some of it takes the form of light. Power utilities do not sell electrons, they sell energy. You supply the electrons. Thus, when you are jolted by an AC electric shock, the electrons making up the current in your body originate in your body. Electrons do not come out of the wire and through your body and into the ground. Energy does. The energy simply causes free electrons in your body to vibrate in unison. Small vibrations tingle. Large vibrations can be fatal. Concept check. What is the source of electrons in a circuit? Unless it is a superconductor, a charge moving in a circuit expends energy. This may result in heating the circuit or in turning a motor. Electric power is the rate at which electrical energy is converted into another form, such as mechanical energy, heat, or light. Electric power is equal to the product of current and voltage. Electric power equals current times voltage. If the voltage is expressed in volts and the current in amperes, then the power is expressed in watts. Figure 3416. The power and voltage on the light bulb reads 60 watts, 120 volts. You can calculate the current that would flow through the bulb as follows. I equals P over V. I equals 60 watts over 120 volts. I equals 0.5 amps. So, in units form, 1 watt equals 1 ampere times 1 volt. If a lamp rated at 120 watts operated on a 120 volt line, you can see that it will draw a current of 1 ampere, since 120 watts equals 1 ampere times 120 volts. A 60 watt lamp draws 0.5 amps on a 120 volt line. This relationship becomes a practical matter when you wish to know the cost of electrical energy, which varies from 1 cent to 10 cents per kilowatt hour depending on the locality. A kilowatt is 1,000 watts, and a kilowatt hour represents the amount of energy consumed in 1 hour at the rate of 1 kilowatt. Think, how much power is used by a calculator that operates on 8 joules and 0.1 amps? If it is used for 1 hour, how much energy does it use? Power equals current times voltage. Power equals 0.1 amps times 8 volts, which equals 0.8 watts. Energy equals power times time. Energy equals 0.8 watts times 1 hour. Energy equals 0.8 watt hours, or 0.0008 kilowatt hours. Will a 1200 watt hairdryer operate on a 120 volt line if the current is limited to 15 amps by a safety fuse? Can 2 hair dryers operate on this line? One 1200 watt hairdryer can operate because the current can provide 15 amps times 120 volts, which equals 1800 watts. But there is inadequate power to operate 2 hair dryers of a combined power of 2400 watts in terms of the current. 1200 watts divided by 120 volts is 10 amps. So the hair dryer will operate when connected to the circuit, but 2 hair dryers will require 20 amps and will blow the 15 amp fuse. Therefore, in a locality where the cost of electricity is 10 cents per kilowatt hour, a 100 watt light bulb can run for 10 hours at a cost of 10 cents, or a cent per each hour. A toaster or iron, which draws more current and therefore more power, costs several times as much to operate for the same time. Notes, solid state lighting may soon make conventional light bulbs obsolete. Watch for the progression of LEDs from flashlights to automobile headlights. Notes, 1 watt equals 1 joule per coulomb times 1 coulomb per second, which equals 1 joule per second. Concept check. How can you express electric power in terms of current and voltage? Summary: electric current. When the ends of an electric conductor are at different electric potentials, charge flows from one end to the other. A current-carrying wire has a net electric charge of 0. Voltage sources such as batteries and generators supply energy that allows charges to move steadily. The resistance of a wire depends on the conductivity of the material used in the wire and also on the thickness and length of the wire. Ohm's law states that the current in a circuit is directly proportional to the voltage impressed across the circuit and is inversely proportionate to the resistance of the circuit. The damaging effects of shock are the result of current passing through the body. Electric current may be AC or DC. With an AC-DC converter, you can operate a battery-run device on AC instead of batteries. In a current-carrying wire, collisions interrupt the motion of the electrons so that their actual drift speed or net speed through the wire due to the field is extremely low. The source of electrons in a circuit is the conduction circuit material itself. Electric power is equal to the product of current and voltage.